Hello, linear algebra student. This video is for chapter 1.8, part 2. So we continue working on transformation and particularly matrix transformation. And we're working on an example where the matrix transformation use a matrix A, 1, 1, negative 1, 2, 3, 7. And we are working on part D, which is asking if 301 is in the range of T. That means can any X map into 301? And we were solving it because this is as if you are solving for finding X, right? So it's trying to solve AX equal to 301. And we actually have entered this into our this augmented matrix into our calculator is 301, and we do a reduced row echelon form. It's become 100, 010, and 001. Now this last row is no solution, right? Because it's a contradiction. So you would get 100, 010. We only have x1, x2, so the last one is a constant, right? So 001 is a contradiction, right? So it means 0 equal to 1 is a contradiction. So that means I cannot solve for any x. So no x, no solution. So this is C in the range, so C is not in the range. In the range of T, you cannot map, no matter how hard you try, you cannot map to 301. So you can see solving equation is very useful. Whatever that you learn in 1.1 and 1.2 is very useful. What about another one? So they have, okay, instead of C, let's do D. Okay, so the last one cannot be, can this one be 3, 2, negative 12? Can it be in the range? So that means solve this now. Okay, do it here. So AX equal to 3, 2, negative 12. So make sure that you understand what they are. This is not the input. They're asking if this is in the range. That means if this is the output. So I want to solve for X, right? So is this solvable? So put 3, 2, negative 12. So 3, 2, negative 12. We just use the same matrix, the coefficient matrix. And then look at our reduced row echelon is 105, 01, negative 1, and 000. So this is not a no solution thing. So a reduced row echelon form become 105, 01, negative 1, 000. So there is solution. So means x1 equal to 5, x2 equal to negative 1. So there is a solution, so we say yes, right? So D is in the range. D is in the range. And the one that maps to it is from this one with x is equal to 5, negative 1. Okay. E. What about what x can map into 0? So T, if someone tells you T of x equal to 0, what are x? So again, this is solving AX is equal to 0. It's a homogeneous solution. I want to solve it, right? So what is X? So all the things that we that we discussed in linear algebra boils down to always solving a matrix equation. So AX equal to 0, how do I solve it? I would use the same augmented matrix, 1, 1, negative 1, 2, 3, 7, but this is 0, 0, 0. Can I find some x that would give map it to 0? Kind of like the x-intercept, right? Y is 0. So I would change the constant sign to 0, 0, 0. I do a reduced row echelon. It is 100, 010, 000. So it is solution, right? There is solution. There's no contradiction. 100, 010, 000. So there is solution, and also there is only one solution. There's no free variable, right? So this is x1 and this is x2. So the one that maps to it would be x1 is 0, x2 is 0. So 0, 0 will map into 0. And there's no other things that would map. So when they say find all, the only one is this one, right? This is the only one that maps into the 0 matrix. Only the trivial solution. Example 2. So let's look at this notation a little bit more. So we're talking about matrix transformation from R4 to R2. That means our input is x1, x2, x3, x4. And then our output is R2, B1, B2, right? So how many rows and how many columns should my A be? Well, my A, so these are all the weights, right? And I'm supposed to get B1, B2. So my row should be 2, right? Should be 2 row. Because the number of rows actually matches the number of entries in the answer, right? Become like this. So this should be 2. So be row 1 and row 2. How many columns should I have? The column would match these because these are the weights of each column, right? A1, A2, A3, A4, right? So this times this times this. So what is this A column then? A is 2 times 4. 2 row and 4 column. So basically, if you have 4 to 2, the A matrix is 2 times 4. 2 row and 4 columns. Okay, so the next things we're going to talk about is linear transformation. So in this page, we talks about transformation, just function, right? What about linear? So a transformation is linear. Now it has nothing to do with matrix now. Just I have some transformation. And if I input u plus v to it, that means I add first and I do the transformation. It's the same as doing them individually. It would be a linear transformation. There's 2 criteria. Criteria number 1 and criteria number 2. It is if I multiply with a scalar matrix, a scalar to my input, it is the same as multiplying the scalar after I do the transformation. So if a mapping obey these 2 rules, then it's called a linear transformation. Notice, had nothing to do with matrix. You can do any transformation. If the transformation is like this, then it is called linear transformation. Okay, so there are a lot of transformations that are not linear. Example would be, for example, I can say a transformation go like this. X1, X2 would become using the T transformation. I would say negative x1, negative x2. This is linear, right? You see how it doesn't involve any matrix, just like that. Just this is my rule, right? I actually can map it to the same column. I start with 2, I end with 2. If I want to, I can do other things too, and you will see that when I do u plus v is equal to t u plus t of v. So if I do x1, x2, and then I have another one, y1, y2, it would, using my transformation, become negative y1, negative y2. It's the same as if I add them, right? So this is a linear transformation. And also, if I multiply a number, it would do that too. So we can prove it this way. It obeys t of x1, x1, x2 plus first y1, y2 is the same as t of individually x1, x2 and t of y1, y2. So this is the first one. So whenever you want to show something as a linear transformation, you have to show the first one and then the second one. If I multiply C with x1, x2, and then I do the transformation. It's the same as c times that also t of the x1, x2. So if you prove that it is the same, then it is a linear transformation. Otherwise, it's just a transformation. What is an example that is not? So an example that is not would be, so this is yes, right? Later on, I'll do another example that shows in details. The one that is not is what? Oh, maybe I'll say x1, x2, the rule is square root of x1, square root of x2. So it is a transformation. I can map anything to this. But you can see if you add them first, if you add x1 plus y1, x2 plus y2, it would map to what? Square root of x1 plus y1, square root of x2 plus y2, right? But it is not the same as adding them individually, right? It's not the same as, square root 1 plus square root 2, square root of x1 and square root of x2, like that. It's not the same. And then square root of x2, y1, this would be y1, and this would be y2. It's not the same. So it is not. So it is not a linear transformation because it doesn't obey these two rules. So so this is the definition. You cannot ask why. So long as they have these two rules, then we say it is linear transformation. Okay. And then because of the definition of linear transformation, we see that if it is a linear transformation, then you must have t of 0 become 0. Okay, t of 0 will not become something else. And also t of, if you multiply c to a vector and then d to another vector and you add them, it's the same as multiply the two vector, the two scalar after you do this transformation. So this is a direct relationship between like mixing them together. Okay, so this is the definition. You have to remember the requirement of the definition. But one thing is I wanted to show is matrix transformation is always a linear transformation. If you're doing transformation and you get your output by doing a times something, it's always a linear transformation. You can prove it. Okay. And and also you can also say linear transformation preserve. We want to word preserve, preserve addition, and also preserve scalar multiplication. So this is the way you remember what is the definition of linear transformation. Okay, so do I have time to prove this? So we're going to prove this. This transformation is x1, x2, x3 become x1, 0, x3. Okay, so is it a linear transformation? Let's try to prove it. So first, prove t of x1, x2 plus t of y1, y2 is the same as t of x1 plus y1, x2 plus y2. So we have to prove this first. Is this the same? So this become what? This become, oh no, x1, x3, right? So because they have three things, x2, x3 plus y3. So what is this? This is x1, 0, x3. This transformation, the answer is y1, 0, y3, right? And what is this transformation? This one is x1 plus y1, 0, x3 plus y3. Are they equal? They're exactly equal. If you add this, that's equal to this. So the first criteria is met. What about the second criteria? If I do c times of x1, y1, and is it the same as if I transform it, is it the same as c times t of x1, y1? It turns out that it is the same because if you do that, then it's just x1, x2, y, x3 is the same.